Howdy, astronomers. Today we're going to be talking about black holes and singularities, primarily the former, and how the former is but one of an example of the latter. I'm doing this a little out of order. Typically, I talk about black holes after I talk about the stellar evolution of high-mass stars. But considering that I'm about to talk about the Big Bang in the next lecture, I figured I might as well talk about black holes and singularities because the two are somewhat related. So much so that Hawking at one point thought that black holes were in fact the birthplaces of quote unquote baby universes. He later retracted that later in life. But the concept of black holes and singularities has been a topic of debate and discussion among the astronomical community for a number of years now. So I thought I would give a primer on black holes and jump off from there. So I hope you enjoy. Okay, howdy y'all. We're going to be talking about black holes and singularities today. As I said in the intro, we're primarily going to be talking about black holes, but I would like you to keep in mind that black holes are the prototype or prototypical singularity. And so when we talk about the Big Bang in the next lecture, we talk about what the Big Bang actually was, or the state of the universe at time equals zero. One of the theories, or one of the hypotheses, is that the universe was in fact a singularity. That is not the only hypothesis that is being bandied around, but it is the current sort of paradigm. So, relating black holes to relativity, you can see here, these are computer animations, or computer simulations rather, of the gravitational waves which are thrown off when two black holes are spiraling into each other. You can see as the pair spirals closer and closer, they will spiral quicker and quicker, which will generate a host of gravitational waves. And then finally, the two will merge in an exceedingly energetic event. And as I stated before, that energetic event can be observed through gamma ray observations and also optical observations as well. And that so if we detect gravitational waves, which we are currently doing with increased frequency, we can look for these optical signatures, these gamma ray signatures, to nail down exactly where it is these objects are located. And this is yet another example. I will talk later about the pieces of evidence that we have for black holes. This is yet but one of those pieces of evidence. Again, we can simulate, or we can anticipate, I should say, what the gravitational wave signature of various objects are, from neutron stars and black holes to theoretically even smaller objects. And the only things that match the signatures that we have observed today are those of black holes and neutron stars. There is no other astrophysical event that astronomers currently know of that will produce the same signature that we're seeing with the precision that we are able to obtain at LIGO and Virgo facilities. So what exactly is a black hole? Well, first let me start off by saying that black holes were first hypothesized as the end result of massive stars. Stars have their own lifespans. They go through evolution very much like a human being does, in the sense that there are young stars, there are middle-aged stars, there are older stars, and then finally there are elderly or dead stars, depending on how you really want to look at it. Now, the end state of a star depends directly on mass, and in actual fact, everything related to stellar evolution depends on stellar mass. primarily timescales and what chemical abundances will result from it, what types of internal changes will occur in the star. All of this depends on the mass of the object. And as I said, the end state also depends on the state of the object. If you're talking about low mass stars, the end state is a white dwarf. If you're talking about intermediate mass stars, then you're talking about neutron stars. And then for the highest mass stars, you're talking about black holes. And as it happens, the line between the end result of a neutron star to the end result of a black hole is very fuzzy. At the present understanding, that line is somewhere between 8 to 20 solar masses, or 8 to 20 times the mass of the sun. But what we can say is, from theoretical models, that the core of the star must be at least 3 solar masses in order for it to collapse down into a black hole. And these occur after what we refer to as a type 2 supernova. And a type 2 supernova is what is known as a core collapse supernova. The star is so massive that when the nuclear fuel runs out of the star, and eventually it will, once you get to iron, you can no longer move iron fast enough in order to fuse it together because of the speed of light. Iron is just simply too heavy to accelerate to those sorts of speeds. Once that nuclear fuel is extinguished or exhausted, then there's nothing to compete against gravity. Gravity always wins. And gravity is going to pull all that mass down, and it's going to pull all that mass down exceedingly quickly, not quickly. There's a U there, not a W. It's going to pull everything down to in incredible speeds. And it's going to, eventually, the core is going to get so degenerate, so dense, that the outer layer materials are literally going to slam into a quantum black brick wall. And that creates an exceedingly energetic event, which is a supernova. But that's not where it ends. That's not where our story ends. The core, that quantum brick wall, continues to collapse into something that is almost incomprehensible. At least the very center of it is, we are not able to describe it physically. Given our current understandings of both relativity and quantum mechanics, the actual center of a black hole, what a black hole actually is still a mystery. But what we can say is that, or at least at the present time, that a black hole is an immense curvature in space-time. If you remember from the last lecture, relativity states that reality is composed of this fabric known as space-time, and that masses will deform space-time if you thought of it in a pseudo 2D, 3D perspective, you can think of it as a rubber sheet. You can place a mass on that rubber sheet, it's going to cause a dimple, it's going to cause a deformation. The larger the mass, the larger that deformation, the lower that rubber sheet is going to hang down, or in this case, space-time. To the point that if you get a large enough mass, then the depth of that distortion is going to become infinitely large, or at least the density of the center of it will become infinitely large. And that is what we refer to as a singularity. And there are plenty of pieces of evidence that indicate what we're talking about. Theoretically, these were theoretically predicted back in the early 1900s, but now we have observational evidence which supports these predictions. Schwarzschild, which we'll talk about later on, was the first to solve Einstein's equations to describe what would happen if the mass, if the mass was large enough and space-time deformed such that it became infinitely dense. That brings us to the Schwarzschild radius. The escape velocity of an object, and everything has an escape velocity. As I'll show in a moment, the escape velocity of an object is directly dependent on the square root of the mass and inversely proportional to the square root of the radius, assuming spherical distribution. Now, what exactly is the escape velocity? The escape velocity is the velocity necessary to leave an object and not be pulled back by the gravitational force and basically stick to the surface of that body. For the Earth, the escape velocity is roughly 11.7 kilometers per second, if I have that right, or Mach 24. That number, that one sticks because it's 24 times the speed of light, or excuse me, 24 times the speed of sound. 24 times the speed of light is impossible. Anyway, so everything that has mass and a radius has an escape speed. Even you have an escape speed. It's just really, really tiny. So it's very easy to, at least from a gravitational standpoint, to fly off of you. For the Earth, as I said, it's, you got to be moving at a pretty good clip. The surface of a star is even more so. The escape velocity is huge. Even though the radius is commensurately larger, the mass is even more commensurately larger. And so the escape velocity is huge. Now, if you talk about a black hole, now the masses of black holes are, well, they can get very large, and we'll talk about supermassive ones in a moment. But there can be stellar massive black holes that are on the order of single to 10 times as large as the sun. Now, whether or not there's a smooth continuum between what we refer to as stellar massive black holes and supermassive black holes, that is still very much of an open question. And there are numerous people trying to bridge that gap. They're trying to find black holes that are hundreds of times, if not just thousands of times the mass of the sun. But remember, it's inversely proportional to the square root of the radius. If the radius of the black hole is infinite, essentially, then the escape velocity far exceeds, even if it's very, very close to zero. If the radius is very, very close to zero, I should say the density is infinite. If the radius is really, really close to zero, then the escape velocity is huge. So how do we define what the escape velocity of a black hole is? And more specifically, can we use this to define the quote unquote surface of a black hole? It doesn't have any physical meaning. And what we find is that with Martin Schwarzschild, he defined the radius or the surface as where the escape velocity of the black hole is equal to the speed of light. So if you were to get closer to the black hole, the escape velocity is larger than the speed of light, which we know at the present moment is the absolute speed limit. Nothing can travel faster than the speed of light as far as we know. So, therefore, black holes are so gravitationally powerful that not even light can escape them. Hence why the name is a black hole, because they don't emit light. And black holes in and upon themselves do not radiate any energy if you kind of ignore Hawking radiation. But even still, I would argue that Hawking radiation doesn't exactly come from the black hole itself. It comes from the production of particles and antiparticles close to the black hole. But that gets into a semantic argument, which I am in no way educated enough, well, smart enough, probably educated enough, but not smart enough to really weigh in on, because that gets into mathematics that are, and I will be free to admit, a little beyond me at this point. Anyway, so the escape velocity is, when the escape velocity is equal to the speed of light, that's what we refer to as the Schwarzschild radius. And we can define the Schwarzschild radius by, I just realized, I hope I'm recording the right screen. Anyway, Let me get rid of this just in case. So anyway, we can define the Schwarzschild radius by basically just reconfiguring the equation for the escape speed. So again, the escape velocity is equal to the square root of 2 times m over r. Again, I'm never going to ask you to memorize this, but if we basically solve this equation such that the velocity, the escape velocity, is equal to c, and we solve for r, we get that r is equal to 2 times g times m divided by the speed of light squared. Now, 2 times gravitational constant divided by the speed of light squared, that's a constant. That's a constant number. And so the Schwarzschild radius depends only on one factor. Doesn't matter how fast it's spinning. It doesn't matter its electric charge. It just matters how massive it is. And that radius is 2.9 times kilometers times the mass of the black hole divided by the mass of the sun. And what that means is that if you double the mass of the black hole, you double the Schwarzschild radius. If you were to multiply the black hole by 1,000,000, then the Schwarzschild radius is 1,000,000 times the mass of the sun, and you start getting black holes where the Schwarzschild radius is the size of the solar system. And that becomes more of an issue or a question when we start talking about massive black holes, and we'll talk about them more in depth when we start talking about active galactic nuclei, one of my favorite subjects beyond young stars. I love me some young stars. Anyway, I know that sounds a little creepy. Anyway, so yeah, moving on. So when we look at what the black hole is, we have the singularity in the middle. We have this essentially no-person land where things theoretically could orbit. And I say theoretically because we're going to get into something called forgot the name, spaghettification, turning into spaghetti. Anyway, I'm sure I'll be able to pronounce it when the slide comes up. So it's arguable if you would actually have any coherent matter within the escape velocity of a black hole, but you might, have something there. And then you have the event horizon. Now, I will say that something there, it gets really, really wonky, and I have heard talks about what's going on in there. And there was one where it was 4 different quadrants, 2 of which you'd get destroyed, 1 of which you would go into an alternate universe, and then the last one is you just get stuck there forever. You just basically sit in the black hole until the black hole itself blew up, assuming that Hawking radiation is true. Anyway, that's an aside. Funny enough, and this is getting away from the talk, I seem to be going on tangents today. One of the sort of sayings around black holes are the black holes have no hair. And what that means is a black hole can be described using only 3 characteristics: the mass, the rate at which it's spinning, and its electric charge, its overall electric charge, whether or not it's positively charged, negatively charged, what have you. The implications of this are that by studying a black hole, you know essentially nothing. You know the mass, you can make an estimate of the mass, you can make an estimate of the spin rate, and you can make an estimate of the overall electric charge for the progenitor star. But everything else, its composition primarily, its temperature, its initial radius, not so much. That information is lost. We don't know where it goes, but that information is lost to us once the black hole forms, which is an interesting concept or interesting consequence of that. When it comes to black holes, it is because they are typically they may not be the most massive, but because they are so infinitely dense, or they are infinitely dense, they create a much larger warping of space-time than an equivalent mass. So for example, if you had a one solar mass black hole and you had a one solar mass sun or star, then the amount of space-time warping would be significantly larger around a black hole than it would be around that star. So for example, the Eddington experiment, the distances between the stars was measurable, but it wasn't, obvious. It wasn't like, whoa, those stars are now really far apart. For a black hole, you get a lot of lensing, and you get a lot of weird things that appear around a black hole. I showed you in class one such thing called an Einstein ring, where if the black hole is in this orientation, and this is a 2D representation, so it doesn't do it justice. If a black hole is directly behind, if a star is directly behind a black hole, or a galaxy is directly behind a black hole, then what you're going to see is not just that star off to the left or off to the right. You're going to see that star up, down, and all directions, and that's going to create an Einstein ring. Now, if it's offset a little bit, if the galaxy or star is not quite at the center, then you're going to get Einstein arcs, as it were. And the other thing to note is, which they don't really do a very good job in this figure, is that the object gets amplified. The amount of brightness of the star or galaxy is larger than if you were to look at that star or galaxy by itself. And so that actually helps us while it becomes weird, or while it becomes, while the amount of information that we can get, such as, the morphology of the galaxy, what it actually looks like without lensing, that gets lost. But we can tell, we can extract other information, such as how red it is, how its color, its temperature, overall temperature, things of that nature, because we can see it more readily than if we were to just observe that galaxy by itself. And therefore, we can observe star or galaxies that are further away. And consequently, where I'm going with this is we can observe galaxies that are far younger than we would ordinarily be able to observe because of a concept called look-back time, which I will focus in on when we talk about the expansion rate of things. Spaghettification? Yeah, I got nothing. I used to be able to say that word, but not anymore. So what this means is, we talked about tidal forces. We talked about the fact that if you have an object that goes within the Roche lobe of a planet or such, that there's a good chance it'll break up. The reason for this is because of the fact that tidal forces are direct or inversely proportional to not just the radius of the object squared, but the radius of the object cubed. It's a much larger effect for than just, say, gravitation, for example. So if you are falling into a black hole, the difference between the tidal effect on your feet is far more than the tidal effect on your head. So you get pulled, you get turned into a strand of spaghetti as you fall into the black hole. Now, if you were to look at the center of your mass, and that was the reference frame in which you were in, then it will look to you as if your head is going up, your feet are going down, and the sides are getting squished in. Hence why you turn into what amounts to a strand of spaghetti. And so this is the question. This is where the question becomes: do masses, or does matter even exist within the Schwarzschild radius? Because of the fact that the tidal forces are so large that matter would be stretched to its potentially breaking point. Now, again, whether or not this applies to subatomic particles, that's another question entirely, which I don't believe we have a very good answer for. Some other weird effects that happen with black holes are what are known as gravitational time dilation and gravitational redshift. Now, let's talk about redshift for a moment, or redshift before. We talked about redshift in terms of motion. We talked about if you are moving towards an object, or what I really should say is that the relative distances between two objects, if that gets smaller, then the light being emitted from either object is going to get bluer. The wavelengths get squashed, the frequency goes up, the light becomes bluer. If the distance gets larger, then the wavelengths get longer, the frequency goes up, down, goes down, frequency goes up, longer wavelength frequency gets higher. No, frequency goes lower. Oh man, brain is fried today. Longer wavelengths, shorter or longer frequencies, then the light gets redder. That's not the only way that you can get redshift. So imagine, again, with mass, it deforms space-time. It causes a stretching in space-time. And this is true for any massive object. You, me, the sun, what have you. Light, which is closer to the gravitational body, is slightly redder than the light which is would emanate from, say, further away from that gravitational body. So, but for us, it's pretty much negligible because we don't have instruments nearly sensitive enough to measure it. For the sun, again, it is, as far as I know of our current technology, it is also imperceptible to the precision that we can see. But for white dwarfs and neutron stars, we can definitely see this effect. And the reason and what the effect is that because space-time is being stretched, the light contained within that space-time is also stretched. Again, the wavelength gets longer. Therefore, the light gets redder. For a black hole, this is even more so, to the point that it becomes blue light will literally become red light, or not even perceptible within the or the peak of the light is not within the visible spectrum. The other thing that's wonky is time dilation becomes a serious factor. As something falls into a black hole, it's going to become redder and redder as it falls into the black hole, but also it's going to look as if it's slowing down. Because of time dilation works not only when things are moving very quickly, but that also time dilation is a thing by getting very close to massive objects. That is the consequence of general relativity as opposed to special relativity, is that these effects that we see in special relativity due to speed are also present when talking about the presence of a large mass. So whenever I talk about relativity, I always couple it to be massive objects moving very quickly or in the presence of large gravitational bodies or large massive objects. So as the object falls in, it becomes redder, and time slows down to the point that it is impossible for us to see something falling into a black hole, because the time dilation would become infinite. Because the object is at the event horizon, where the speed of light, where the escape velocity becomes the speed of light. So we'd see a big strand of spaghetti just hanging there. But also weird is the fact that a black hole is simply a mass. So what that means is while the local environment of a black hole gets stretched to all heck and back, as the black hole when you're close to the black hole, the space-time gets very, very distorted. But when you're far enough away from the black hole, then the distortion that you would experience is the same as if you had any object of that mass. So, for example, if we were able to magically, if say Scarlet Witch was able to magically snap her fingers and turn the sun into a black hole, the Earth would freeze, but its orbit would be the same, assuming that the black hole was one solar mass. So a black hole doesn't suck. Black hole just simply distorts the space-time in a local way. Well, local to the Schwarzschild radius of that black hole. But it doesn't suck in everything into the universe. It's simply a mass. It pulls in things equivalent to the gravitational influence that it would have if it were any other mass. Now, as I said, localized, this is localized, or orbits that are fairly close to the Schwarzschild radius would be destabilized and they would fall into the black hole. And we can see that effect with the sun. Mercury's orbit is slightly destabilized in the fact that it's not going to fall into the sun, but its period is highly elliptical and and precesses around the black hole. The point of aphelion, the point at which Mercury is furthest away from the sun, actually rotates around in its direction with the solar system. That doesn't happen with the rest of the planets because quantum mechanically, there's no explanation for why it should. And so I suppose I should preface this by saying that we cannot detect the precession of the other orbits because they're far enough away that the curvature of space-time is essentially does not produce that effect to a large extent. Now, as I said, stellar massive black holes are anywhere between 3 to 100. And the 100 we haven't directly observed, but that is essentially the end state for the largest mass stars that we know of. That again, theoretically, that we know of. Stars that are greater than 150 solar masses are going to be spinning so large that they literally blow us. Well, let me back way off that statement. A star that is 150 solar masses, or 150 times the mass of the sun, is going to be generating so much nuclear energy that it's going to blow itself apart. It's also going to be exceedingly rapidly rotating, but the primary bit is that it's producing so much nuclear energy that it will literally explode. So if you had a 150 solar mass, if it was right on that edge, and you had core collapse, then it would form a black hole from 100 solar masses of thereabouts. We can detect stellar massive black holes from things like X-ray binaries, for example, which I'll talk about in a moment. We know of stellar mass black holes. We also know of supermassive black holes between 1 million to 1 billion solar masses. Now, as I'll talk about in a second, we know that there is a supermassive black hole at the center of our own galaxy because we can directly observe the effect that supermassive black hole has on the surrounding stars at the galactic center. Just recently, we're able to directly measure the mass of one of these black holes at the center of another galaxy. The difference is there are things called active galactic nuclei, which I'll, again, go into depth later on. But they produce an exceedingly large amount of energy, just one of the most energetic things in the universe. They power the galaxy in a sense. The energy being generated is because of frictional forces or thermal forces or thermal emission from the disk, a disk of material which presumably were stars at some point, but were tidally ripped apart, that disk of material creates, through something analogous to friction, creates a tremendous amount of energy. So again, this energy is not being emitted by the black hole itself. It's being emitted by a disk of material surrounding that black hole, which is moving relative to each other. So the inner parts of the disk are moving faster than the outer part of the disk, which creates a sort of a friction or shearing effect. And the picture of that, if you can Google the M87, you will, or image of a supermassive black hole, you will see the image of a dark center and a red ring surrounding it. And that red ring corresponds to the material that is infalling into the black hole. We believe that supermassive black holes exist at the centers of all galaxies, or at least all major massive galaxies. It's like I said, intermediate black holes, which we would expect to be in the centers of small galaxies, we haven't seen any measurements for, because one, small galaxies tend to not be active galactic nuclei, or do not tend to have active galactic nuclei. Primarily, as a guess, there are just not enough stars in there to rip apart. There are not enough stars close enough to the black hole to rip apart to create such a large disk to generate that kind of energy. So we can't measure it that way. And small galaxies are so faint and so far away that we couldn't possibly resolve the inner regions yet in order to do the same experiment that we did with the Milky Way galaxy. We can't see the individual stars moving relative to each other. So intermediate black holes, which we would expect to see at least down to some minimum range, we haven't been able to really measure because of the observational challenges that we have. But again, we expect to be able to see them. What we're seeing here is direct evidence of the supermassive black hole within the Milky Way galaxy. This evidence was provided by the Keck telescope using a very sophisticated adaptive optic system. And what you're seeing is those red and green dots are individual stars moving at breakneck speeds around nothing. And what I say by nothing, what I mean to say is that given the observations that we have of optical observations that you can see there, there is nothing that is producing any sort of light over almost all wavelengths. And so the only explanation for why those stars are moving so quickly is that there is something supermassive there. And because it is shedding no light, it is a black supermassive something. Therefore, the best explanation for what is gravitationally slinging these stars around is a supermassive black hole. Now, I've been speaking primarily of the left-hand side. The middle one would be observations from the Keck using a next-generation adaptive optic system, which is currently being designed. And then the one on the far right is using the 30-meter extremely large telescope. As I like to say, astronomers are brilliant at naming things, plus an AO system. The lines that you see are the completed orbits that we can measure. And so for Keck and current AO, we can completely define 2 orbits. With Keck plus the next generation AO, you can see that that number moves up to half a dozen. And then with a 30-meter telescope, it moves to dozens. And so this gives you an example of just why larger telescopes are needed in order to study the heavens effectively. X-ray binaries. X-ray binaries are basically the first piece of evidence that we had for black holes. And again, this is very much like supermassive black holes in the fact that you have an accretion disk. You have a disk of material surrounding the black hole, creating a tremendous amount of energy. In this case, it's not stars being ripped apart per se. Well, in a way, it is. So what's going on is, and we'll talk again more about this as we talk about stellar evolution and when we talk more about stellar evolution. There was something else I wanted to say there and completely blanked. But anyway, with stellar evolution, stars grow, and if the star grows large enough, then the outer parts of its surface are going to essentially exceed that Roche lobe. So the outer part of the star can actually escape into space if it's given enough, if the velocity is pointed outward, if the velocity of the particles are pointed outward. In the case of binary stars, what can happen, or in this case, a star going around a black hole, the star is massive enough that when the material comes off of the companion star, it's gravitationally attracted to the black hole and falls into the black hole. So it's in a way ripping material off of the companion star, or at least the material which composes the accretion disk is material that came from that companion star. And again, what we're talking about is a disk of material which is rotating very rapidly, but rotating what we refer to as differentially. Material which is rotating, which is in the inner part of the disk, is moving at a much faster rate than material that is in the outer part of the disk. And when we talk about the energy which is emitted, or the energy which is generated from that shearing effect in the outer part of the disk, that energy is close to the radio or infrared parts of the spectrum. As you move closer and closer in, you move into the visible part of the electromagnetic spectrum, the UV part of the electromagnetic spectrum, and finally into the X-ray part of the electromagnetic spectrum. And that's where it gets key, because for a star like this red giant, which we see on the screen, we have no expectation or really explanation why it would be a strong X-ray source. X-rays come from exceedingly hot objects, and a red dwarf is actually really, really cold, comparatively speaking. So there's nothing to form, there's no mechanism for a red dwarf, or red giant rather, to emit X-rays. The only way that we know of, or I should say the most probable explanation for X-ray emission, is this accretion disk model. And again, because we can optically see, because we have measurements of or instruments precise enough to see the star spectroscopically and optically visibly, there's nothing there. There's nothing, no other companion that we can spot. Nothing else that has the spectral configuration of a star. So we only get the spectrum of the companion star and that of a disk. We don't see an object, therefore it's a black hole. Or again, the most probable explanation is that of a black hole. I've already talked about supermassive black holes. Again, this is a theoretical picture of one. As far as I can tell, this is again a simulation where you have a disk of material surrounding the inner part of a black hole. It creates more energy. The accretion disk creates more energy for the AGN. The energy that is created by this disk of infalling material is by far larger than the energy generated by the billions of stars within the galaxy itself. So when we look at the galaxy, most of the light that we're seeing, or a good fraction of the light that we're seeing, is generated by an area about the size of the solar system. It's crazy to think about. And lastly, what I'll end with is these radio lobes, or these galactic jets that we see. Again, this is this is material which is highly energetic. It's moving at near relativistic speeds, which we can measure based on the redshift of the light. I know that light looks blue, but in fact, the spectral lines are highly redshifted. And really what you're seeing is energy which was created in the X-ray part of the spectrum that's redshifted into the optical. So it's blue because, well, it's hot, but it's blue because it was so hot when it generated, and the gravitational redshift has caused it to become blue in our spectrum. And that blue, that very energetic light, or very energetic material, gets blown out into space, hits the very slow moving interstellar material that is, well, between stars or interstellar. That material is going to slam into that material and create these radio lobes. These are lobes which can be seen optically, but are much brighter and much more distinguished in the radio parts of the spectrum. And again, we only see these jets around AGN. We only see this phenomenon around a disk surrounding the supermassive black hole, because again, one of the consequences of material falling into a black hole, which has a tremendous magnetic field, is that some of that material falls in, but some of that material goes along those magnetic field lines and gets blasted out the north and south magnetic poles of that object. And because they're supermassive, the speeds at which this material gets blasted is near relativistic, and it's large enough. The amount of material is sizable enough that we can actually measure it from millions of light years away. So with that is my lecture on black holes and singularities. We will talk more about singularities in the next lecture, which will cover the Big Bang. I promise this time. I've been promising a lecture on the Big Bang for some time now, back even on my Rob World channel or playlist. Really, I will be doing it this time. Promise. Pinky swear. All right. That's all from me. Peace out.